Okay, well, so I'm going to continue with the subject or the topic of statistical decision theory. And, well, thanks for the questions you were asking. I will encourage you to ask as many questions as you want. Because I remember I heard from someone that questions are a public good, and because of the externalities, they tend to be underprovided in equilibrium. So I don't really know what's the solution to the under provision of public good problem. I guess I would need to subsidize you somehow. But just keep that in mind. Maybe just internalize the fact that questions are good. And so the other thing is that I like doing stuff in the board, not because I'm lazy with PowerPoint or the LaTeX or stuff, but just because I think it gives good timing for me, just so that you can digest the things that I'm writing. And so, if there's something that doesn't make sense, really ask me, because the intention is that everything should be clear. So what I want to talk about today is the two general principles that decision theory has for thinking about how to recommend or pick a decision. Okay, so it's the base principle and the minimax principle. And so what I'm going to try to do today is there is a very general way of thinking about how to set up or how to find a base decision rule for general decision problems. And so I want to show to you today how that derivation looks like and what are the ingredients that you need in order to derive this, and talk a little bit about the good things about it and the bad things about it. So for the minimax principle, there's really no such a general way of solving a minimax problem. So what I'm going to do is I'm going to give you kind of like a general construction that connects the worst case principle, the minimax principle, with the average performance principle, to kind of like argue that if you know how to solve these ones, you can always figure out bounds for the optimal values of these minimax problems. So that's why I'm going to start here. But then once that I'm there, I'm going to move to a particular example just to give you a sense of how one could think about solving these problems. I think that the limitation here that there's no theorem, it's not mine. If you see lectures from famous people, say that this part is more like a very like artisan. It's just like problem by problem. You need to figure out like interesting ways of thinking about it. Okay, so just a couple of reminders about the notation that I set up last time. Remember, I have a decision problem. That means that there's a parameter space and there's parameter statistical model, payoff function. I was using this idea of expected utility to denote what would happen if you pick decision rule D and you pretend for a second that the true state of the world is theta, and you compute the average payoff, assuming that X, the data, has distribution P of theta. Okay? So then I told you also that I was working with utility, but you could define an analogous quantity that I'm going to refer to as risk. And risk is going to be very similar. I start with a loss function. I have a decision rule. And again, I fix a particular value of the parameter in the parameter space. And I'm going to be looking at the expected loss, where the expectation here is over the possible values that X can take, and X has distribution P of theta. Okay? So the results that I'm going to be working with today, I'm going to focus on mainly on risk. So I'm going to be thinking about the loss just because that's a more conventional notation that you'll find in a math stats book, but the things go, I mean, just you can move back and forth. It's really not a problem, okay? So, okay. So perfect. So I think the complication in trying to figure out what's a good decision rule appears because you fix the decision rule and then the performance, how much expected utility you get or what's the expected loss that you will get, is going to vary as a function of theta, right? So if you fix d, this gives you a function that is telling you payoffs or rewards or losses as you move theta around. So if you think about it, the problem of comparing two decision rules is equivalent to comparing risk functions or expected utility functions. And so more frequently than not, these functions are going to cross somewhere. So there are going to be some places in which the risk of certain decision rules is going to be lower, but some places in which the risk is going to be higher. And therefore, you're going to need to think about how to deal with those instances. Right? So one way of doing this is by thinking about averaging the performance of these rules according to some distribution. So what I'm going to do is, I'm going to pretend for a second that pi is the PDF of distribution over theta. I'm going to use this distribution to really just average the values of theta, the values of the parameters in the parameter space, as you will see. So this is the PDF of distribution over theta, the parameter space. And so I can define the average risk and maybe let me just call this the pi average risk that is also called the base risk of a decision rule D. The following way. So I'm going to start with the risk function. And as I said, the concern here is that as you fix the decision rule and put in different values of theta, this gives you different payoffs. So at some points in the parameter space, the decision rule seems it's doing okay, but in some other places it might not be performing that greatly. So what I want to do is consider the expectation. Now I'm going to write this thing. So I'm looking at the risk function, but now I'm averaging over the different values of theta that appear in the parameter space according to some distribution. Now, because the things I'm going to be doing some algebra, you might be wondering, well, Pepe, why do you need to say that this is a PDF? You could have had a discrete distribution, and it's true, everything works out. It's just like some points I want to be explicit about what this expectation is. So RD depends on theta, so pi is already a PDF over theta. So I'm going to be really thinking that this is just the integral over this space. Yep. Does that make sense so far? Okay, excellent. Okay, so then I think I can just give you a definition. So it's going to be base rule. this pi base rule. So I'm going to say that a decision rule D star is base if it solves the problem a decision rule is base for distribution pi over theta if it's the rule that minimizes the average risk as you average the parameters according to the distribution pi. Okay, and so, I mean, the first comment is obviously definition of base rule here depends on pi, so that's just part of the definition. So one thing that connects to some of the questions that you were asking yesterday that I think made a lot of sense is that the typical definition that you would find is of this form where the space of decision rules that you consider is not restricted ex ante. You're thinking about all functions that map the data into the action space, but which is the thing that I'm going to leave in the board. But it's very easy to amend this by thinking about situations in which instead of defining base as the rule that the decision rule that minimizes the average risk over all decision rules, you do this minimization over a constrained class of decision rules. Okay? But so that could be by really taking this definition and just putting D belongs to some set. Does that make sense? Okay, excellent. Well, so what I want to argue now is that it's like the tension and release part of the presentation. If you think about the type of optimization problem that we're trying to solve here, it should look like intimidating and difficult to solve optimization problem. The reason being that the choice set in this optimization, the choice variable in this optimization problem is a function, right? So, you know, I mean, grad students these days, you have definitely more teched up than my generation, but you know, when I was in grad school, I really can only solve optimization problems for which I could take derivatives. Yeah. The function depends on the objective function that I'm trying to optimize has as an argument a function. Just my head starts, you know, to crack just because how am I going to take first order conditions? Right, so there has to be something about the problem that I'm describing, because I'm telling you that there's a general solution that somehow allows me to simplify this problem. And what I want to show you, what I refer to as a general way of solving for these problems, is what I'm going to present next. So it's just like a very simple way in which you can simplify this problem to just get maybe simpler to express program that defines the solution, provided that the action space is not too complicated. Okay. So on another comment that it's I think worth making at this point, maybe should I save it for later? No, I think I'm going to do it now. If you, I think there was a question yesterday about at what point exactly is this decision maker relying on data, right? And so what I was trying to do is that, or to tell you is that the definition of decision rule is allowing this decision maker to condition its choice of action on the particular data that gets realized, right? But if you think about the type of operation that is being represented here, this operation is happening kind of like at an ex-ante level. So this is a decision maker that has access to a statistical model, somehow came up with an idea of how to weight the parameter space. And because I'm going to be providing a function for from the data to the action space, I don't really need to think about exactly what's the data that I have at hand, right? So I could solve this problem from the ex-ante perspective, just thinking, well, whatever data that I get to see, you know, on average, I'm going to get this payoff if this were to be the true parameter space, the true parameter in the parameter space, and then I just have to average things out. Okay, so part of the trick of how to make this a little bit more operational is going to be moving a little bit from this ex-ante perspective to this ex-post perspective. And so this is what sometimes creates tension between, you know, a person that would describe himself or herself as a frequentist and a person that would describe himself or herself as a Bayesian. But here, I view it purely as a mechanical device that is going to allow me to solve this particular problem. Right? I think that the framework of statistical decision theory, in principle, I feel that it's kind of like agnostic about what type of, you know, school you're going to be pledging allegiance to. As long as you know, there's a model and there's a parameter space, you can do whatever you want. Yeah.
So you mentioned that we're doing this ex ante.
Yeah.
Would one way can we choose a pi to make it look as though we're doing it ex post, in that I only put weight on data for which it's possible for that data to have generated the x that I actually see, and in that case, would we call that ex post? Or?
Could be, but so maybe the case that we're going to be thinking about is cases in which the different values of the parameter space, they don't really rule out certain data realizations. So we're going to be playing a game in which, think about a normal model, right? So say you have a real valued random variable that it's a normal with mean mu and variance 1, say. The fact that you have choose different values of the normal, whether it's normal 0 or normal 1, does not really rule out realizations in the real line. So in that case, by choosing pi, I cannot fully rule out you know, certain data realizations, even if you're dogmatic on a particular value. But maybe in other cases, it could happen. Okay, so let me just do these. So I think the algebra that I'm going to do is very simple, and I think it's one of these things that I think it's worth seeing once in your life, and then just putting it somewhere in your notes, and then you can come back if needed. Anyway.
Can I ask like a big picture question?
Yeah, of course.
So we're trying to extract this decision rule.
Yeah.
And, like, emotionally, I want to understand, like, I have a d of x, right, and x is something from like a sample, and I want to understand like the sampling variation in this like random variable, which are going to be the decisions that arise through this function.
Yeah.
I guess like, since we're working in this kind of ex ante framework, and I've decided how to handle different draws through my loss function, I don't really need to be worrying about that. Like, this framework sort of tells me how to construct the decision rule from an ex ante perspective, so I'm not thinking about that sampling variation. I shouldn't be. Is that kind of?
But the sample variation here, it's already, it's present, right? Because in this definition of, in the definition of risk or expected utility, you're doing this step in which you say, well, gee, my model says that the data that I could see could look like this. So you're already doing this, what would be my average payoff if I were to pick this particular rule? So there's something of that still here. And I think for me, like, the only thing about doing it ex ante is that it makes it explicit that, say, when you report an estimator, or whenever you estimate something, you typically say, well, I'm estimating the parameter of this model by doing maximum likelihood or generalized method of moments. So there's clear that thing that you're reporting, there is a function that maps the data into whatever you got. So in all these things that we're doing, they're always ex ante, right? Like you're committing to the use of something.
Does it matter what space are we extracting the decision rule? Like, kind of what space, what functions? Like, decision rule is a sort of
Function from
So,
data
like,
to actions.
yeah, but
Yeah.
like, kind of, what do we need to characterize the space of function that we are working in? Like,
So what I said that in this version that I'm going to give today, the thing that I have in mind is that any measurable function, really, the only thing that you need is that you know, the data that you have maps nicely into the action space. So there has to be some restriction on these things, but other than that, I'm not imposing anything. I'm not asking for just continuity or higher order derivatives or anything like that. It's just measurability. Yeah. Yeah, Stasia.
So, for example, if you have additional restriction already
Uh-huh.
variable, so you have that sort of a constraint optimization case,
Absolutely.
would that still be considered? Would that still be defined as a base?
Yeah, what I was saying is that I would, if I had to do it, I just tweak the definition a little bit because it would be based within a particular set, and you would just need to be thinking about how to solve that optimization problem because now D cannot be picked in a non-restricted fashion. You need to, and you'll see that I mean, the reason why I don't present the restricted case is because the unrestricted case is the one that has an easy solution. The restricted case, I cannot give you something as explicit as what I'm going to show you next. Does that make sense? Okay, perfect. So let's do it. Okay, so perfect. So so essentially what I want to argue is that I'm going to write explicitly what is a candidate solution for that problem, and then I'm going to show you that that candidate solution solves that problem, okay? So what I'm going to do is, so remember I've been using the definition of a model as, so we have defined a statistical model as a collection of distributions p theta, right? So now, again, just to help myself simplify the notation, I'm going to assume that there's a common dominating measure so that all these things can be expressed as densities. Really think about the normal mu variance sigma squared case thing. So I'm going to denote f of x colon theta to be kind of like the probability density function associated to P of theta. Okay, so does that make sense so far? I mean, I'm just started with these abstract, these probability distributions, but now I'm just making it a little bit more concrete so that I can give you easier to digest notation. Okay. So, and I'm going to argue that, so I'm going to say claim so let the star of pi, because the solution of that problem depends on pi, be the decision rule that assigns to each data realization x following action. So I'm going to set up A star as any action that minimizes the following problem. Okay, so just a couple of things that are just mechanical to just double check that what I'm writing makes sense. So first, this one has to be a mapping from data realizations to actions. So what I have to give as input is data realization, and what I need to get out is some action. So I'm fixing the data realization. So this is X is fixed. So I double check that this is not integrated out in any way. It's just really fixed. And what I'm asking you to do is now to take the loss function, evaluate it at a particular action, and integrate it with respect to these two distributions, f and pi. So the integral here is with respect to theta. The evaluation of this function depends on A. So I'm assigning for this particular realization x, the decision rule is going to take me to any of the A's that solve this problem. Okay, and so I'm going to tell you a little bit about the interpretation and how this is like implementing Bayes' rule. But first, before getting there, is that the simplification that I was talking about is that we started with a set of functions that map data into the actions or action space. And so instead of taking the optimization problem directly on these functions, now I'm optimizing over the action space. So as long as the action space is not complicated or too complicated, and for example, in some of the problems that I described, like say parametric estimation, where you have a finite dimensional parameter that you're interested in, you would be optimizing over those parameter values. So that's an optimization in a finite dimensional space. If I'm looking at these treatment choice problems where I need to pick action 1 or action 0, the choice it just has 2 elements, so I'm just optimizing over these 2 things. And there are other problems, and I hope to show you a couple, in which this action space can be complicated as well. It could be in both functions. And then I need to think about how to do something similar to what I'm about to show you to simplify my problem. But this is now not an ex-ante take on the problem, because it's fixing a particular value of x. So the problem transformed from ex-ante averaging over all possible realizations of x to an ex-post problem where I'm fixing the particular realization of x that I want to assign the decision. Does that make sense? Okay. So okay, and so then what I'm just going to show you is the algebra of why this claim is correct, right? So the claim should be that this decision rule, so D star solves the thing that I call 1. So that's the claim. Yeah, question? Yeah, that's the claim. Yeah.
So this integral is the expected pi average risk.
What's that?
This integral is the pi average risk.
This integral that I have over here is this integral over here.
Yes.
Pretty much. You see that I mean, what appears here is the loss, what appears there is the risk. So there's one step that you need to use to connect them, but yes.
What risk is the loss? Okay, so it's this.
Yeah, no, risk is the expected loss.
So we have the expected loss.
Not quite, because the expected loss is relative to the values of x. There's no integral here with respect to x. But it's almost there, and so that's kind of like I like showing this is such a simple proof that, just like that's why I'm saying you need to see it once in your life, and then you don't have to worry about this ever again. Okay, so here's the argument. So essentially proof, or sketch of the proof, if you wish. So it's going to be very simple. Just going to do it very mechanically, which is unraveling just definitions, right? So I'm going to take, I'm going to start from the objective function that appears over there. Right? And I'm going to write it exactly as I have it in the display before, which is right? So that's just really definition of how the way we define these average risk or pi risk or base risk. And so now I'm going to open up the definition of what's the risk function, right? So I'm going to keep this integral over here, and this one is another integral, right? So I'm going to just open a big parenthesis. So I'm going to try to respect here the pi theta and d theta, and what I'm going to put inside is, well, the loss, right, of a particular action, a particular decision rule. And just going to note that this is being integrated with respect to x. Does that make sense? Okay. So then, going to be thinking about a case in which this thing is finite. Decision rules for which this is infinite, they're never going to be selected, because if this is infinite for a particular decision rule, it would never be the one that minimizes, provided that there's another one for which this is finite. Okay? So I'm going to be thinking here that I'm putting all the d's for which this thing is integrable, that this thing is finite. But the thing that I forgot to put in here is that the integration here is over all possible data realizations. I had this notation to denote the space of values that the data set can take. Perfect. And because of finiteness, what I can do is just change the order of integration, right? So now I'm going to integrate. The outside integral is going to be over data realization. The inner integral is going to be over values in the parameter space. And so this one depends on theta, so I cannot fully put it out. So I have to keep it here. So this is integrated with respect to theta, and then I'm integrating with respect to x. Does that make sense? So then this is the objective function that appears in here. So suppose that you pick the action for each x, you pick the action that makes this integral the smallest that it can be. Then that's going to put a lower bound on what's the risk of any other decision rule. And therefore that is the sketch part, is the issue with measurability. How do we know that this correspondence is measurable? But leaving that aside for a second, then what we've shown that is that the rule that assigns, that picks actions in that way, is going to be the one that minimizes risk for this particular pi. Does that make sense? So I think this one we can just close it. Yeah.
So you're just talking about how we needed that left-hand side to be finite so we can stop the integrals. And I just wanted to ask, I probably should have asked this yesterday.
Yeah.
When you were setting up the notation, the action space wasn't changing with the parameter.
Yeah, the action space, we're keeping it fixed.
Okay. One of the reasons why I didn't ask it then was if it were the case that the action space did change with the parameter, then I can imagine defining
Just remember, that would be really conceptually very tricky because the whole point here is that when you're asked to take an action, you do it, absent knowledge of what the parameter is. So if the action space were changing with the parameter, the fact that the action space is changing would reveal information about what the parameter is, right? So that would be really a framework that is outside this part.
So if I were to change, write down the utility or loss function in a way where I assign infinite loss to actions taken outside of the parameter-specific action space, could I get myself back into this framework?
That thing, if you're just thinking about writing u of a of theta and somehow at some point making it infinity for certain values, you can get back to this, but then the caveat is that, those type of integrals, depending on how you're setting up the actions, you might be taking actions that sometimes lead you to these infinite laws, and that could mean that, because you do not know the parameter at the beginning, you can be looking at decision rules that very frequently send you there, and that integral would not be fine.
Okay. And consequently, we wouldn't be able to spot the...
Flip the order of integration, yeah.
Thank you.
Yeah, cool. So that's a base rule, and so let me just do one very simple connection. So I'm gonna keep this one over here. Just minor thing about interpretation is that the objective function that appears there. Now that it looks like remember this integral is taking over theta. So this is a PDF, so it's no negative. This guy is a PDF, so it's no negative. And again, one thing that I could do without really changing this objective function. So here, remember that the thing that I want to be picking over is A. Everything else is integrated out. So I could rescale this problem. So I'm going to take this object over here and standardize it so that the thing that appears in the top is a PDF itself. So it's already no negative, so I just need this to integrate all the way to 1, right? So one thing that I can do this is just figure out what's the mass of these. Right, so this doesn't depend on A, so it doesn't really change anything else, and it's really a constant because X is fixed. So for the purpose of this optimization of A given X, it's not changing anything. And so this guy over here, now you can think of this as being, a version of the posterior distribution of theta given X. So I'm going to just roll it slightly to the side. And so another way of thinking about what you're doing is that if you want to solve or figure out what's the rule that gives you the best average risk for a distribution pi, that's equivalent to figuring out what's the action that for each theta minimizes posterior loss, or the expected value of the loss, where the expectation is taken with respect to the posterior distribution of theta given x. Right, that makes sense, and that I think that connects very quickly statistical decision theory with some of the things that Pierre was talking in the previous things, that to compute, to be able to integrate over theta, sometimes I cannot do this analytically, so I need to do this integration numerically for fixed A. And so that's why, for example, from the perspective of decision theory, knowing about all these sampling schemes like Monte Carlo Markov chain could be very useful, because it's an input that I need in order for me to be able to solve my decision problem. It's not that I fundamentally think that theta is a random variable or whatever. It's just mechanically, if I want to solve these, optimize this average performance, that boils down to doing this. Yep.
Is that where the name Bayes decision rule comes from? Because
Yeah.
all we have known is the name Bayes.
Yeah, so pretty much it's like the idea that that distribution that you take over the parameter space, now you view it as being a prior. What it's being described here is what typically is called the posterior. So this is the statistical model, this is the prior, this is the posterior distribution, updated based on the realization of x. And then the loss, A is fixed because you're deciding what A I should be picking. But theta is unknown, but now you can average theta according to the posterior distribution. And that's a base rule. Does that make sense? Yeah.
So there's absolutely no difference between being Bayesians and being not Bayesians, but optimizing by average.
Yeah, so I mean that thing, I think it's a thing that it's helpful to keep in mind, or at least to me, you can always justify these or type of procedures as just being procedures that are guaranteeing that the average performance of this decision rule according to that way is going to be okay. And so I think it puts everything on equal footing. Right? Does that make sense? Okay, so I'm gonna give you a quick okay, so I started with kind of like this idea that, well, we're so used to be thinking about average and average utility, average payoff, all these things. So we do this all the time. But if you think about it, if I really take these guys as my primitives, there is a way of thinking about kind of like what could be viewed as a necessary condition for optimality. So I'm going to give you a definition, and that I hope relates or somehow triggers connections with notions of Pareto efficiency, right? If I start with this point, with this risk function, right, that is taking different values for theta, there is a sense in which I would like to be using a decision rule that is Pareto efficient, in the sense that it might be possible to find another rule that improves at some values of the parameter space, but that it cannot do this without damaging the performance somewhere else. Okay? So that's kind of like the connection to Pareto efficiency. You can, allocations are Pareto efficiency if you can, a group of people, you take something from someone that harms that people. So you cannot make everyone happy without making someone unhappy, right? So that's a general thing. So I'm going to be thinking about something similar here. So there's a couple of definitions that I think are helpful. So there's one has the name of dominance. So decision rule D is dominated if there exists another decision rule different than D, such that the risk of D prime at theta is smaller than RD theta for every theta in the parameter space with strict inequality for at least one theta. Right, and so, I mean, to me, this is not a hard to buy definition for the idea that there are certain decision rules that I don't want to be ever nearby. Right, so if it's truly the case that I can find another decision rule that improves performance everywhere in the parameter space with strict inequality somewhere, then I want to know what that rule is, because certainly I would like to replace D by D prime. I feel that way. Maybe you have different preferences. You could feel differently. But so this is something that really speaks directly about performance of decision rules at different points in the parameter space without having to bring in this notion of averaging yet, right? So similar definition that sometimes appears in this literature, it's the notion of admissibility. And so this one is easy to define, because once that you know what dominance is, you say that a rule is admissible if it's not dominated. That makes sense, right? It's kind of like admissible, or it's reasonable to think about using it if it's not the case that you can improve the performance of it uniformly over the parameter space with some strict inequality, right? So D is admissible if it is not dominated. Okay, so kind of like another cute little result that again, to put in your book of notes of things that it's okay to see once, but you never once again have to worry about it. So there's kind of like a nice implication that if you're a person that is interested in this average performance, and the weight that you're using for assessing average performance is not too crazy, any rule that you solve by using that base principle is going to be admissible. Right, so I'm going to give you a sketch of a proof of that claim. But I'm just going to write the claim so that you see that there are a couple of things that I need to take care of, because there's this thing that, well, you know, what if you're looking at a crazy point in the parameter space and just it's one, you just have one of these weights that just looks at one particular point. I mean, isn't it possible that even if you figure out what's the best thing for that point, you could be improving everywhere else? And so that's possible sometimes. So there's another claim here then. So I'm going to say that suppose that the risk function is continuous at theta for every fixed t. So now continuity here, I think continuity is always a tricky concept. When theta is an object of finite dimension, continuity is exactly what you would expect. You just have a function of many variables, and you're expecting that if you have two values of theta that are nearby, the function is going to, function evaluated at these 2 points is not going to be that far away. So it's a typical definition of continuity. It gets a little bit more complicated if theta is a space of infinite dimension, which, as we talked about, we are allowing in principle. But there are ways of doing this, and so there's the definition of the continuity of this for every fixed decision rule. It's going to make sense in a bunch of cases. So suppose also that pi has full support on the parameter space. If theta had finitely many values, full support is very clear what it means. It's like every point in the parameter space needs to have a strictly positive probability under this weight. If theta is, say, the real line or the plane, as it would be when I have a normal model, for example, full support, put in quote unquote, because I think one needs to be a little bit, give a little bit more details on what one means. But one way of thinking about it is that for every point in the parameter space, any open ball around it has positive probability. Again, we are getting too much into detail of the topology here, but it helps to consider cases in which theta is an open space, so that for every point that I take, there exists one of these open balls that contains it. And that's not the case if this were to be in the boundary, but if it's open, every point is interior, essentially. So I'm putting this quote unquote, but it's essentially what you would think in the real life, that if you someone tells you that the parameter space is any value in the real line, you want to have a distribution that has, allows for any realization of theta in the real line.
I'm wondering how restrictive that might be if I can redefine what my cap theta is, so that any point in which pi has zero mass on that theta, I can create a cap theta tilde that removes such points. If it's the case that pi of theta is equal to zero, then I wouldn't be caring about that theta in some sense. So can I always ensure that pi will have full support on the parameter space if I choose a parameter space carefully enough?
Remember, the parameter space is typically, that's kind of like a primitive of this problem, right? Because it's one of the ingredients of what's the statistical decision problem. What we're choosing is the pi.
Right.
So the pi, you can pick whatever you want. So all I'm asking is that among all the pi's that you can pick, just pick one that satisfies these restrictions. If you have other pi's in mind, there might be theorems that look like these with different conditions. Just like you would need to have some sort of restrictions, just because of what I said. Like if you go to this extreme case where all you care about is performance at one point, if you find a solution to that, there's no guarantee that that's going to work out globally, right? And this notion of admissibility that I have over here is global. Okay? Yeah, perfect. So, okay, perfect. So these are the assumptions that I need, and then so the claim is then any base rule is admissible. that we're, yeah,
And admissibility says nothing about prior, so we can't
no,
start it.
yeah.
And on the prior says something that
Yeah. Which I think, I mean, again, this is, as you can see, I'm not, pledging allegiance to the Bayesian school in any way. I think I like the decision theory framework because it kind of like always made sense to me. But then, these rules seem to be like, well, I put a pi over the table, and if the pi is not that crazy, it seems like I do end up getting a global property, which is this, it's a weak guarantee, but it's a valuable guarantee nevertheless. It's like, there's nothing else that really improves upon what you're doing uniformly. Just that I kind of like that I'm, always writing papers on methodology and stuff. It's like, well, what if I come up with an idea that, turns out that it's uniformly bad. So I think some of these things protect you a little bit against that. Okay, but so then let's do sketch of proof. Okay, so the argument is going to be very simple. So the statement is essentially base rule, or a solution to the problem that I had over there implies admissibility. So I'm going to do the contrapositive. I'm going to argue that if a rule is not admissible, then it cannot be a base rule. Okay. So I'm going to prove not admissible implies not base rule. Okay, so I start now with the rule is not admissible. So there exists decision rule d prime such that the risk of d prime theta is smaller than or equal than the risk of d at theta for every theta. And because of the definition, this has to happen with some strict inequality. Okay? Perfect. Let me just, I'm going to call theta star the point at which you have a strict inequality. I'm just going to write it like this. Strict inequality. Let me also call this rule, this is supposed to be the base rule with respect to prior pi. So that's the thing that I'm violating, right? So that the admissibility is the admissibility of this guy. So, okay. So the risk function is continuous, right? It's continuous for any, that's part of the assumptions. It's for any fixed decision rule. So that means that if I look at the difference in payoffs that I get from R, from d prime and d pi, if I look at this difference in for every theta that are, or for a bunch of thetas that are nearby theta star, the continuity is going to imply that this thing is still going to know the sign, right? Performance here is going to be strictly smaller than here for every theta that is near, close enough to theta star. Right, so so the way I'm going to say this is that there exists, by continuity, there exists a ball b theta star such that this happens for every theta in b theta star. right? But then that means that, if we look at the average payoff that you get by using d prime, and remember here the average payoff is computed according to pi, right? So I'm going to be able to decompose this integral, and I'm just going to write to avoid repeating the notation, I'm just going to break this integral into this ball and whatever is not in this ball, right? Yep.
In the previous statement, where you're invoking continuity,
Yeah.
after the such that, maybe I just didn't see, but should that be an inequality? RD prime theta is less than or equal to RD star theta?
Less than or equal?
Sorry, all the way second to the last line. Okay.
Thank you.
And also just to clarify, in the statement of the claim,
Yeah.
we wrote that the risk function is continuous at theta. I initially took that to mean that there's
Continuous at theta for every fixed d.
for every fixed d.
Yeah.
I took that to mean that there was some parameter theta.
Continuous at theta, it's for every theta. It's continuity for every theta.
Okay.
Continuity for every theta.
Okay.
Yeah. Right, but then I'm pretty much done because so the first part of this integral is going to be strictly below the performance of the supposedly optimal rule. Now, the full support of the prior is important here because the only way in which I can guarantee that this integral counts is if this guy over here has positive mass. So that is going to give me strict inequality here. And then everywhere else, I knew I had at least, as much risk as I had with the other one. So these two are going to be strictly smaller than the average performance that I get under d star pi. That means that there's no way that d star pi could have solved the average risk minimization problem. Does that make sense? Yeah. Excellent. So let me do one more thing just to do a little bit of connection with hyperplanes and convex sets and just get it back. I was not planning to do it, but Guillaume inspired me in the morning. So, there is there's of course a geometric way of thinking about these things. Not really good with geometry, but I think for this problem, think for a second that there are only 2 points in the parameter space, right? So the risk function, instead of being a function, is just a vector in R2. Okay? So now, imagine that, let me see if I get this one right, but imagine for a second that, so the risk profiles now can be placed somewhere in this plane, right? I can think that what I'm going to be putting on the x-axis is the risk of an arbitrary decision rule evaluated at parameter theta, we call it theta naught. And what I'm going to be putting on the x-axis is the risk for arbitrary decision rule at theta 1, right? So instead of having the function, what I have is this risk profile. Now, a decision rule maps into a vector here, right? So if I draw a little vector here. That would be, say, the risk profile corresponding to decision rule D. But I could put maybe another one over here, and that could be the risk profile corresponding to a decision rule D tilde. And you can think about the exercise of, imagine that you move over all possible decision rules that you can pick. How would this space is going to look like? And so there are a couple of things that are interesting. So the space of decision rules, because I have no external restrictions, it's a convex space. If you just take one decision rule and take another one and take the linear combination of them, if the action space that I have is convex, they're going to be valid decision rules as well. Right? Because one maps into some actions, the other maps into some actions, the action space is convex, you're back to this thing. So it's a couple of lines just to prove it, but you can show that the space of possible risk profiles that you can attain is also going to be convex. Right? So it's going to look like some sort of convex set. Right, and yeah, I'm just going to do a general depiction of a convex set. Let's just say. Right, there are other properties that one can show. This space, for example, is going to be closed as well. So now closed is easier to define because you have points in the plane, so you can just use the topology of the plane to define closeness. Yeah, so perfect. So, so one thing that it's helpful, I think, of this picture is that, let me do this thing here properly. It's kind of like if I fix a decision rule D, like the one that I picked over here, and I want to visualize or just think whether this decision rule is dominated or not, then I think this picture helps me thinking about that, right? Because if just ask you, would you say this decision rule is dominated or is it admissible? And what would you say? It's dominated. It's anything, I mean, this is convex and everything that is in here is corresponds to a particular decision rule, then you could move anywhere in this direction and improve the performance of this decision rule uniformly. Perfect. So remember, I'm in R2, right? So the average performance or the average risk is essentially just an equation of the form, say, pi 0 times R D theta 0 plus pi 1 R D theta 1. And I mean, you've seen these things, right? It's like this is not negative, they add up to 1 because they're weights. So it's a hyperplane or a budget constraint because we're in R2. So how do I depict that one? Well, just line like that, right? So the problem of figuring out what's the rule, the decision rule that minimizes average performance, it's kind of like these problems that we did in micro, right? Just trying to figure out what's the point in the set that gives you the smallest value of these, the smallest coordinate for this hyperplane, right? So for instance, in this case, the solution of this problem is going to be something like, these are supposed to be parallel, if not to the adjustment, but they're parallel. So this is the solution pi, and so essentially the proof that we had over there is saying that if you really have one of these solutions, then it's going to be admissible, because if it were not the case, you could move a little bit towards the inside of this set, towards the outside, towards the boundary of this set, and you could improve the average risk. Right, so that's kind of like a geometric version of the algebraic argument that I had over here. But I mean, one thing that I think also invites you to think about is that in this example at least, you can give kind of like the other direction of that theorem. Remember, we kind of like show that you have a base rule is admissible, but then there's other side of that relation, right? Like, is it the case that a rule that is admissible, it's necessarily based for some prior? And so, just go back to your supporting hyperplane theorems, right? Have a closed convex set. And for every point that is admissible, you're going to be able to find a prior such that that prior makes this rule base. Yeah, okay, questions?
So how do we, like in the case where in the morning we talked about the linear programming case, we know that the gradient of the decision curve is going to be like, you know, parallels across this plane. So like you intersect at one of the intersect the feasible region at a vertex, and you have the like the optimal solution. But in this case, like how do we necessarily know that we're going to have a line that intersects the we're going to have like the decision rules which are parallel to the like to some line there. Like I guess I don't quite understand how does the why is the gradient function in this case it's going to be a straight line like
Why is the gradient function? So do you believe to me that this is the objective function?
yeah. No, like
This is the objective function. So what's the gradient of this thing? I mean, isn't the gradient budget constraint, right? I give you px times x plus py times y. What's the gradient of that line, right?
Okay, so you're treating the entire risk thing as a variable instead of like
I mean, I'm treating this that you know, if I fix the decision rule, that gives me one particular evaluation of this, right? But say you fix the constant and you think about what are the set of all possible risk profiles that would put me here, right? That's kind of like the pxx plus pyy equals income.
So this is a space where the risk is linear with respect to the total risk is linear with respect to like.
But that's always the case because I'm defining average risk. Average risk, right?
Sure. Okay.
So it's always linear because it's the integral.
Gotcha. Okay.
Yeah. But with the other thing, just like with the discussion, the things that Guillaume was talking about in the morning with the linear program, we were looking at polytopes, right? So it's an intersection of finitely many equalities and inequalities. So this is a general convex set. So the boundary of these things could be smooth, right? So there's no room for having these points that define so it's an infinite dimensional support function. Here is an infinite dimensional object. Yeah, okay. So we're good? Okay, awesome. So perfect. So then I think we can get started with Minimax, and we'll do more Minimax, I guess, tomorrow. Let me erase some of these things. Let me see which one I can erase. Let me erase the proofs. Just keep these definitions. Yeah, and if you are just curious about, maybe just, admissibility, in case you haven't heard of this before, yeah, there are a couple of interesting results about admissibility out there. Probably one that is now maybe relevant because of all this interest in shrinkage estimators and Stein shrinkage and all the cool things that Chet is doing. You can just look at Stein's paradox and think about what happens when you have a multivariate normal and you have more than 3 components. Just one realization of a multivariate normal, and you want to think about a good estimator using mean squared error as the loss function. And yeah, you'll get these really mind-blowing results that say that as long as you have more than 3 dimensions in your vector, just reporting the sample mean is going to be dominated. That's and some of this shrinkage stuff dominates the mean, the sample mean. So that's pretty crazy. But then there are a bunch of other maybe more recent applications. I say Andrew now has a couple of papers looking at inadmissibility of GMM under some conditions, but it's these notions, very classical notions. Okay, so let me just open the discussion for next time. So I'm going to be looking at 2 other, so it's the minimax principle, but the minimax principle is going to have 2 different phases that I'm going to show you. One that I'm going to be focusing on is ones that we're working directly with a loss. So say, let's just put this one. So I'm going to do the same thing. So I'm going to start with the expected loss of a decision rule, RD theta. But now, instead of looking at average performance of a decision rule, I'm going to look at rule's worst case performance. So what do I mean by worst case performance? Well, there's a parameter that tells you how poorly or how okay the rule performed. So I'm going to look at the largest value that the risk can take as I move theta in the parameter space. Right, and then using supremum instead of maximum, just, not always attained, but it's the same thing. So I'm going to just remind you that I could be using max over here. And then what I'm going to try to do is think about, this depends on the decision rule, right? So I'm going to try to optimize the worst case performance, meaning that once that I know what's the worst case performance of a particular decision rule, I'm looking for the rule that gives me the best worst case performance. So this is the mean. Right, so the definition is a decision rule D is minimax if it solves this problem. That makes sense. And so kind of like a similar comment to the one that I made before. So here the space of decision rules is not restricted, but you can think about a version of this definition where the set of decision rules over which you try to solve this minimax problem is different than the set of all particular functions, right? And the only thing that I would change in this definition is that I would need to put here explicitly the set of decision rules over which you're optimizing. Does that make sense? Yep. So just one quick comment about this. There is a version of the minimax criterion that it's going to look very similar in terms of these inf and sup operations, but in which the risk function is going to be defined relative to what it's called regret loss, or just regret. And so I'm going to define a regret loss in two cases. So suppose that instead of working directly with the loss function, we are working with the utility function. Yeah? Suppose that we start with U instead of L. Okay, so one thing that you can always define is, I'm going to use calligraphic L. So starting out from the utility function U, I'm going to define a loss. And remember, loss for me are really just maps from actions and parameters to rewards. So I'm going to define it in the following way. Perfect. So I'm going to think about two problems. So one of them is kind of like the payoff that a person that actually knows the parameter space, the value the value theta in the parameter space that I'm using to evaluate this loss. I'm going to think about what would be the payoff or utility that this person would get, and I'm going to use that number as a benchmark to see how far I am from that oracle action. So the way I'm going to do that is I'm going to consider the not feasible problem of maximizing the payoff for a fixed theta over all actions in the action space. Right, so this is an oracle quantity because it presumes that I know what the value of theta is. Right, and I'm going to use this as a benchmark. So I'm going to take this number and I'm going to use this as a benchmark to see how I'm doing. I mean, this is always non-negative, just because this supremum is going to be larger than this for NEA. And also, if it creates confusion for anything, you can use a different notation for that. It's just I'm optimizing here over all actions, but I'm evaluating this at a particular action that you took. And so this type of operation is typically called a regret loss. And you can do this for the utility, if you start with utility, but you can also do this for any loss that you start with, right? I mean, if I could define something similar, if I start out with a loss function, right? And I just need to change a little bit how the benchmark. So instead of looking at the largest loss, the oracle would try to make this loss as small as possible, right? So I could have something like the infimum of L A tilde theta over all actions. And now I can use this as a benchmark of performance. Yeah.
Just to make sure, is this exentic or exposed? So is it average over the data?
Remember, there's no data. This is just a primitive. It's just the loss function and the utility functions. They're defined just as mappings from actions and parameters to rewards. So there's no data.
Okay.
But it's not exposed. It's just like this is a primitive to your problem. It's kind of like the thing that I was explaining yesterday. That, well, maybe one way of thinking about payoffs for estimation problems is like whatever estimator you're going to report, just a number or a vector. I just want to see how far that is from the true parameter. So it's just one of the ingredients of the decision problem. For a decision problem, the way that I define it is just you have parameter space, you have statistical model, you have a payoff function. So when you apply the minimax criterion to loss that was built using this regret principle, you typically add the qualifier that the rule, instead of just being minimax, you say that it's minimax regret. But so that presumes that if you started with a utility or a loss, you're using now the thing that appears inside the expectation when you define the risk function, it's one of these regret losses. But other than the term regret, these are the same. I mean, just mathematically, they're the same things. It's a mini-max problem. Okay, so tomorrow we do a little bit more of how do we actually go around solving this problem. I mean, the big thing is that solving these problems is hard because in the other case where we're doing average, we're able to transform the problem to an ex post problem, which makes things easier. But here, we can't do that. So we just need to think about ways in which we can solve this thing or approximate the solutions. So it gets a little bit trickier, but we'll talk about that tomorrow. I think we're good? Awesome.